Hey everyone, Dr.Mungli here. So in this video, let me explain you all about gluconeogenesis process. So note that gluconeogenesis seems to be a difficult topic for the students, but actually it is not as difficult as you think, because all you need to remember here is which all the irreversible reactions in glycolysis and how to reverse them. That's what is gluconeogenesis is all about. And also you need to just know like what all the precursors for gluconeogenesis process. So anyway, so I'm going to make gluconeogenesis as simple as possible, and so that you all get to know what all the high yield things in gluconeogenesis process. So if you are new to my channel, so consider subscribing to my channels if you are not subscribed already. So please consider subscribing so that and also don't forget to click this bell icon so that you get regular notification. And also if you like the video, give thumbs up. And also if you have any questions, so feel free to write that in the comment so that I can get back to you and answer if you have any questions or any doubts related to gluconeogenesis process. So let's get into gluconeogenesis. So as I was saying earlier that gluconeogenesis actually it is a reversal of glycolysis reaction. So I have written glycolysis here. So as you can see, glycolysis, it is the conversion of glucose into pyruvate. See, the glucose is all the way converted to pyruvate. That's what is the glycolysis which is going on in the cytoplasm. So in conversion of glucose all the way into glycolysis, as I told you, so you got to remember three irreversible reactions in glycolysis. So those irreversible reactions I have mentioned in red arrows here. So rest of all the reactions are reversible. So you don't need to actually go into the details of those reactions as long as you know glycolytic reactions. So I have a video on glycolysis, so you can take a look at that video to have a better understanding of gluconeogenesis, or if you have an understanding of gluconeogenesis and you are good in glycolysis, so you can just go ahead and continue this video. So what are those irreversible reactions in glycolysis? So the irreversible reactions in glycolysis, so we have a very first reaction which is catalyzed by glucokinase and hexokinase, glucokinase or hexokinase enzyme. So this is the very first irreversible reaction in glycolysis, converting glucose into glucose 6-phosphate. Our second irreversible reaction in glycolysis is catalyzed by phosphofructokinase. Phosphofructokinase 1, that is PFK1. Phosphofructokinase 1 converts fructose 6-phosphate into fructose 1,6-bisphosphate. And the third irreversible reaction in glycolysis is pyruvate kinase enzyme catalyzed reaction. So overall we have three enzymes here, so which catalyzes irreversible reactions in glycolysis. So glucose to glucose 6-phosphate, it is glucokinase hexokinase reaction, fructose 6-phosphate into fructose 1,6-bisphosphate, phosphofructokinase 1 enzyme, phosphoenol pyruvate into pyruvate, we have pyruvate kinase enzyme. So these are the only three irreversible reactions that you need to take care so that you can reverse pyruvate all the way back into glucose, because other than these three irreversible reactions, all other reactions are reversible in glycolysis. That means you can use same enzymes that were involved in glycolysis to reverse all the reversible enzymes. So we don't need to bring in a new enzyme to reverse those reactions. They all work under flux. Like if the flux of the product is more than the substrate, it just reverses the reaction. So all we need to know here is how to take care of glucokinase hexokinase reaction, phosphofructokinase 1 reaction and pyruvate kinase reaction. If you know how to take care of these three reactions, to reverse the reaction here. So, that means we basically understanding of gluconeogenesis becomes much easier. Now, let us see how that happens. So, I have written here. So, let us reverse pyruvate back into glucose. So, pyruvate into glucose by pyruvate kinase enzyme, it is not possible by reverse. It is a irreversible reaction, you cannot simply reverse it. So, we need to bring in new enzyme. Only thing is, we do not have any reaction any enzyme that can take pyruvate back into phosphoenol pyruvate. Simply we do not have any enzyme, any such enzyme which can reverse pyruvate into phosphoenol pyruvate. We do not have any enzymes. So, just remember that. So, that means we cannot convert pyruvate back into phosphoenol pyruvate directly because we do not have any enzyme there. So, how to do that? So, there is a way to take pyruvate back into phosphoenol pyruvate. So, it means we need to convert first pyruvate into oxaloacetate. Pyruvate will be converted into oxaloacetate, and oxaloacetate will be converted into phosphoenol pyruvate. So, basically we have one of the two reactions which will take pyruvate back into phosphoenol pyruvate. So, pyruvate into oxaloacetate, it will be done by enzyme pyruvate carboxylase enzyme. Pyruvate carboxylase enzyme converts pyruvate into oxaloacetate, and there is another enzyme which will convert oxaloacetate into phosphoenol pyruvate, and that is phosphoenol pyruvate carboxykinase enzyme. PP is phosphoenol pyruvate, carboxykinase, phosphoenol pyruvate carboxykinase, PEPCK. So, this is the enzyme that will take oxaloacetate into phosphoenol pyruvate. So, this way pyruvate can be reversed into phosphoenol pyruvate. We cannot take pyruvate back into phosphoenol pyruvate in one step because we do not have any enzyme that can do that. That is why what we need to do is, what happens in our cell is, especially in the hepatocytes, and also remember gluconeogenesis predominantly will go on in the hepatocytes, that is in the liver, and to certain extent it can go on in the kidney, or to a small amount it can go in the small intestine. Now, pyruvate has to be converted first into oxaloacetate, and oxaloacetate can be converted to phosphoenol pyruvate. So, this way we have made a glycolytic intermediate phosphoenol pyruvate. So, the reversal of pyruvate kinase step in glycolysis, that is conversion of phosphoenol pyruvate into pyruvate. If you want to reverse this back into phosphoenol pyruvate, so we cannot use pyruvate kinase. That is why what we have done, we have used two enzymes. One is pyruvate carboxylase, other is phosphoenol pyruvate carboxykinase, and we have converted pyruvate back into phosphoenol pyruvate. From phosphoenol pyruvate we will have to go, so all these reversible reactions will take phosphoenol pyruvate into fructose 1,6 bisphosphate, and fructose 1,6 bisphosphate going into fructose 6 phosphate. In the glycolysis, see this phosphofructokinase 1 enzyme which is catalyzing a irreversible reaction here. Conversion of fructose 6 phosphate into fructose 1,6 bisphosphate is an irreversible reaction. In order to reverse conversion of fructose 1,6 bisphosphate back into fructose 6 phosphate, we cannot use the same enzyme. We have to bring in a new enzyme, and that new enzyme, it will be fructose 1,6 bisphosphatase enzyme. So, I am going to write that here. So, the name of the enzyme is fructose 1,6 bisphosphatase. Fructose 1,6 BPase, fructose 1,6 bisphosphatase. Substrate is fructose 1,6 bisphosphate. You are going to remove phosphate from the first carbon, and that is why the name of the enzyme is bisphosphatase. So, we are going to get fructose 6 phosphate with this enzyme. So, this is how we can reverse conversion of fructose 1,6 bisphosphate back into fructose 6 phosphate by removing the phosphate from the first carbon. That is done by fructose 1,6 bisphosphatase enzyme. So, with that we got fructose 6 phosphate which is reversed into glucose 6 phosphate. Now, we are coming to the first irreversible step in glycolysis, catalyzed by hexokinase and glucokinase. So, we cannot use the same enzyme to reverse glucose 6 phosphate back into glucose. So, we need to bring in a new enzyme, and that new enzyme now it is glucose 6 phosphatase. So, glucose 6 phosphate will be converted into glucose molecule by glucose 6 phosphatase. Glucose 6 phosphatase, basically phosphatase, it removes phosphate from the 6th carbon, glucose 6 phosphatase, that is the enzyme. So, glucose 6 phosphatase will take care of the reversal of glucokinase exokinase step back into glucose. So, like this 3 irreversible reactions in glycolysis will be taken care in gluconeogenesis by 4 enzymes. So, for pyruvate kinase step we need 2 enzymes, pyruvate carboxylase phosphenyl pyruvate carboxykinase to take pyruvate back into phosphenyl pyruvate. For phosphofructokinase 1 step reversal we have this fructose 1,6 bisphosphatase, and for glucokinase exokinase step reversible we have this glucose 6 phosphatase. These are the corresponding enzymes for 3 irreversible reactions in glycolysis. For pyruvate kinase we have pyruvate carboxylase CK, that is phosphenyl pyruvate carboxykinase. For phosphofructokinase 1 we have fructose 1,6 bisphosphatase. For glucokinase exokinase step we have glucose 6 phosphatase. And also remember that glucose is a 6 carbon molecule. So, as you all know we have 6 carbons in glucose. Glucose has 6 carbons. So, that means you all know pyruvate is a 3 carbon molecule. So, in order to make 6 carbon glucose, so that means we need 2 pyruvate molecules. 2 pyruvates need to be converted into 2 phosphenyl pyruvate, 2 pyruvate into 2 phosphenyl pyruvate, and 2 phosphenyl pyruvate together will give 1 molecule of fructose 1,6 bisphosphate because it is a 6 carbon molecule. So, 2 phosphenyl pyruvate, which is 3 carbon. So, 2 of them is 6 carbon. Like that we make 6 carbon fructose 1,6 bisphosphate, which is going all the way to glucose. So, this is how we are going to make glucose from pyruvate. So, this is basically, these are 3 important enzymes. So, I am going to add like there may, so basically 3 irreversible reactions in glycolysis will be taken care by 4 enzymes. So, there are 4 enzymes here. What are the 4 enzymes in gluconeogenesis? We have pyruvate carboxylase, phosphenyl pyruvate carboxykinase, fructose 1,6 bisphosphatase, and glucose 6 phosphatase. Out of these 4 enzymes, the most regulated enzyme in gluconeogenesis is fructose 1,6 bisphosphatase. I am going to explain you the regulation later. So, now how to get this pyruvate, or what all the other substrate that can make glucose molecules. So, that we are going to see in subsequent slides. Now, to continue, so we have gluconeogenic precursor. So, let us see what all the gluconeogenic precursors that we have. So, the gluconeogenic precursors can be like first one is alanine, amino acid alanine. So, whenever person goes into fasting state, especially when the person is not eating food for like 12 hours and going into 24 hours onwards, so where there is increase in glucagon, and this glucagon hormone what it does, and in the deficiency of insulin what happens is there can be breakdown of skeletal muscle, especially when the person goes for fasting, going into starvation like more than 24 hours, going into 48 hours, something like that. There can be breakdown of skeletal muscle proteins, and these skeletal muscle proteins gives amino acids, and these amino acids one or the other way they can be converted into alanine and glutamine, and alanine is the predominant amino acid that gets out of the skeletal muscle. So, alanine is taken to the liver, and in the liver alanine can be converted into glucose molecule. So, alanine is a gluconeogenic precursor. Now, anaerobic glycolysis, whenever like red blood cell where the glycolysis is anaerobic, or like skeletal muscle, like severely exercising skeletal muscle, strenuous physical activity, where lactate is returning back to liver. So, in the liver lactate can be converted into glucose molecule, that is the gluconeogenesis process. We are going to look into that. So, the third precursor for gluconeogenesis is glycerol. You know, glycerol is part of triacyl glycerol present in the adipose tissue. So, whenever person goes into fasting state, so again hormone glucagon we will activate an enzyme called hormone sensitive lipase enzyme. This hormone sensitive lipase enzyme, it's going to break triacyl glycerol into 3 fatty acid and a glycerol molecule, and glycerol is taken from the adipose tissue to the liver by in the blood, and in the liver this glycerol is converted into glucose by gluconeogenesis process. So, glycerol is a precursor for glucose formation. It is a gluconeogenic precursor. Number 4 is propionyl CoA. Now, the propionyl CoA, it is coming from different sources as a metabolic product. So, propionyl CoA can come from oxidation of odd number carbon fatty acid, branched chain fatty acid, bile acid synthesis, catabolism of valine, isoleucine, threonine and methionine. So, I have a video on sources of propionyl CoA. So, if you are interested, you can watch that video. So, propionyl CoA coming from those sources, so will be converted to glucose. So, propionyl CoA is one of the gluconeogenic precursor. So, these are 4 important gluconeogenic precursors. So, we are going to see how exactly alanine is converted to glucose, lactate is converted to glucose, glycerol is converted to glucose, and how propionyl CoA is converted to glucose molecule. So, let us see how lactate is converted to glucose. So, in order for lactate to convert into glucose, so first thing is lactate has to be converted into pyruvate. So, lactate is converted to pyruvate molecule. So, this will be done by lactate dehydrogenase enzyme. So, the name of the enzyme is lactate dehydrogenase. So, which is sometimes referred as LDH, lactate dehydrogenase. So, during this process what happens is NAD plus is going to get into the reaction. There is a need for NAD plus here. NAD plus enters into the reaction and is reduced into NADH plus H plus. So, NAD plus entering into the reaction and NADH plus H plus is made here. That is how lactate is oxidized into pyruvate. Note that lactate is a 3 carbon molecule and pyruvate is a 3 carbon molecule. So, with basically to convert lactate into pyruvate, there is a need for NAD plus. You need to remember that, it is very important for gluconeogenesis to happen, like in the gluconeogenesis process, especially in the liver. So, this lactate has to be converted into pyruvate molecule. So, that needs NAD plus. Without NAD plus, lactate dehydrogenase simply cannot work optimally, because it needs a oxidized molecule NAD plus to reduce that into NADH plus. That is when lactate is converted to pyruvate. Once you get pyruvate, so I have already explained you in earlier slides, this pyruvate so basically pyruvate goes into the mitochondria and in the, so let me explain that now. So, pyruvate, it enters into the mitochondria. So, in the mitochondria pyruvate is converted to oxaloacetate by pyruvate carboxylase enzyme, and oxaloacetate will be converted to phosphoenol pyruvate by phosphoenol pyruvate carboxykinase, and that is how it will go back into gluconeogenesis process. Anyway, I am going to write that separately in subsequent slides. So, this is how lactate is converted to pyruvate, and pyruvate now it is ready to go into gluconeogenesis. Let us keep it like that now. So, I am going to now explain you how exactly pyruvate is going into gluconeogenesis once I finish explaining gluconeogenic precursor. So, remember lactate dehydrogenase needs NAD plus as the coenzyme here. So, there is a requirement for NAD plus there. Now, how alanine is converted to pyruvate? So, the conversion of alanine into pyruvate. So, alanine undergoes transamination reaction to make pyruvate molecule. So, it is a transamination reaction which is a reversible reaction done by alanine transaminase. Alanine transaminase enzyme is the one that will convert alanine which is a 3 carbon molecule. Alanine has basically, it has amino group, carboxyl group alpha carbon and the methyl group side chain. So, basically alanine is giving its 3 carbon as pyruvate there, and this pyruvate it can basically go into gluconeogenesis process. Okay. So, pyruvate is now ready for gluconeogenesis. This is how alanine is converted into pyruvate molecule. Now, let us see how glycerol is converted to dihydroxyacetone phosphate, which is eventually going into gluconeogenesis. So, as I told you, glycerol is part of triacyl glycerol. So, tag triacyl glycerol. So, in the basically triacyl glycerol, it undergoes lipolysis in the presence of glucagon, and also glucagon is going to activate an enzyme called hormone sensitive lipase, hormone sensitive. So, that means it is sensitive to hormone, that is glucagon. Hormone sensitive lipase enzyme is going to break triacyl glycerol into 3 fatty acids plus a glycerol molecule. That is how we get glycerol. This glycerol enters into the blood and then it is taken to the liver, and in the liver glycerol is converted to glycerol 3-phosphate, and that is the first reaction, glycerol 3-phosphate. It will be done by enzyme glycerol kinase enzyme. Glycerol kinase enzyme uses ATP and releases ADP. So, there is a consumption of ATP there. So, that is how glycerol is converted to glycerol 3-phosphate by glycerol kinase enzyme. Now, the glycerol 3-phosphate will be converted to dihydroxyacetone phosphate, DHAP, dihydroxyacetone phosphate. So, that is what is DHAP that I have written here. So, dihydroxyacetone phosphate formation from glycerol 3-phosphate, it will be done by glycerol 3-phosphate dehydrogenase enzyme. This glycerol 3-phosphate dehydrogenase. Remember, this is glycerol 3-phosphate dehydrogenase, not glyceraldehyde 3-phosphate dehydrogenase. Glycerol 3-phosphate dehydrogenase. So, in this reaction there is a need for NAD plus again. So, NAD plus is necessary for this enzyme and it will release NADH plus H plus. So, again there is a requirement of NAD plus here, just like how I explained conversion of lactate into pyruvate by lactate dehydrogenase, there is a need for NAD plus. In the same way, conversion of glycerol 3-phosphate into dihydroxyacetone phosphate, there is a need for NAD plus. That means to continue gluconeogenesis or the gluconeogenesis process itself, it needs NAD plus. There is a necessity for NAD plus here, remember that. So, this is how glycerol is converted to dihydroxyacetone phosphate. So, there are 2 reactions which are important here. One is glycerol kinase reaction, other is glycerol 3-phosphate dehydrogenase reaction. So, once you get dihydroxyacetone phosphate, you know it is a glycolytic intermediate and it can be reversed into glucose, because you know glycolysis. So, dihydroxyacetone phosphate 3 carbon molecule. So, this 3 carbon molecule, it can be converted to glyceraldehyde 3-phosphate, one of the molecule. So, of course, like you need 2 glycerol molecule to make 1 glucose, because glycerol is a 3 carbon molecule, glucose is 6 carbon. Of course, you need 2 glycerol, which is converting into 2 molecule of dihydroxyacetone phosphate. In that, one of the dihydroxyacetone phosphate will be converted into glyceraldehyde 3-phosphate, that is also a glycolytic intermediate. So, now the glyceraldehyde 3-phosphate will combine with dihydroxyacetone phosphate to make fructose 1,6-bisphosphate, and fructose 1,6-bisphosphate will go back into fructose 6-phosphate, glucose 6-phosphate, and then all the way to glucose. So, that is how glucose can be synthesized from glycerol molecule, 2 molecules of glycerol. Now, how propionyl CoA is converted to succinyl CoA. So, I already told you sources of propionyl CoA. I have a video. So, link for that video is appearing in the upper right corner right now. So, please watch that video for sources of propionyl CoA. So, I explained the sources of propionyl CoA as Bob needs vitamin M. So, Bob needs vitamin M. So, that is the sources. Please watch the video. So, I don't have, I'll take long time for me to explain here again. That will basically dilute my gluconeogenesis topic for now. So, kindly watch that video if you really need that information for sources of propionyl CoA. Anyway, so how the propionyl CoA is converted to succinyl CoA. So, the propionyl CoA again it is a 3 carbon molecule. Propionyl CoA is having 3 carbon. Propionyl CoA is converted to methyl malonyl CoA. Methyl malonyl CoA, and methyl malonyl CoA is converted into succinyl CoA. So, succinyl CoA is a TCA cycle intermediate. Anyway, so before that let me explain what are the enzymes. So, propionyl CoA to methyl malonyl CoA. So, there is a carboxylation reaction going on here. So, carbon dioxide getting into the reaction, and it needs biotin, vitamin biotin, magnesium it needs, and also it needs ATP. So, the reaction is catalyzed by enzyme pyruvate propionyl CoA carboxylase. Propionyl CoA is a substrate which is undergoing carboxylation. That is why carboxylase, propionyl CoA carboxylase. That is how propionyl CoA 3 carbon molecule is converted into methyl malonyl CoA, which is a 4 carbon molecule. Now, the methyl malonyl CoA will be converted to succinyl CoA by methyl malonyl CoA mutase. Methyl malonyl CoA mutase. So, this is the enzyme that converts methyl malonyl CoA into succinyl CoA, and this enzyme it needs adenosyl cobalamin as the vitamin as the coenzyme, vitamin B12 in the form of adenosyl cobalamin. So, we have succinyl CoA, which is a 4 carbon molecule. You all know succinyl CoA is a TCA cycle intermediate. So, succinyl CoA is converted to succinate, and succinate can be converted to fumarate, and fumarate is converted to malate, and malate will move out of, all these reactions are going on in the matrix of mitochondria. So, the malate can move out of mitochondria into the cytoplasm and become oxaloacetate, and oxaloacetate can be converted to pyruvate. Oxaloacetate will be converted to in the cytoplasm, oxaloacetate in the matrix of mitochondria. Malate is going out of mitochondria into cytoplasm, converted to oxaloacetate, and oxaloacetate in the cytoplasm will be converted into phosphoenol pyruvate, and this phosphoenol pyruvate is a it's a glycolytic intermediate, 3 carbon molecule, and this 3 carbon phosphoenol pyruvate will be converted all the way into fructose 1,6 bisphosphate, which is converted to fructose 6 phosphate to glucose 6 phosphate, and ultimately to glucose. That means we need 2 molecules of propionyl CoA to make 1 molecule of glucose. Okay. So, reactions that are needed here, so important ones in conversion of propionyl CoA to glucose. Of course, we need propionyl CoA carboxylase, methyl malonyl CoA mutase, and once you get like oxaloacetate to phosphoenol pyruvate. So, but that reaction conversion of oxaloacetate into phosphoenol pyruvate. So, we need that enzyme called PepCK, phosphoenol pyruvate carboxykinase enzyme, and of course, after that we need a fructose 1,6 bisphosphatase, and then we need glucose 6 phosphatase. So, these are the enzymes that are needed for important ones for conversion of propionyl CoA into succinyl CoA. Now, let us see important enzymes in gluconeogenesis process, individual ones. So, that means let us go from lactate. So, let us begin with alanine. So, for 2 alanine converting into 1 glucose, alanine is converted to pyruvate by transaminase enzyme alanine transaminase. So, not really the high yield one, but of course, that enzyme is needed. So, alanine is converted to pyruvate by alanine transaminase ALT enzyme, alanine transaminase, and pyruvate is it has to enter into mitochondria because pyruvate cannot go back to phosphoenol pyruvate directly. Pyruvate enters into mitochondria to become, so in the mitochondria pyruvate is converted to oxaloacetate, and conversion of pyruvate into oxaloacetate, it will be done by pyruvate carboxylase enzyme, pyruvate carboxylase. So, pyruvate carboxylase, where carbon dioxide entering into the reaction. So, 3 carbon pyruvate is converted into 4 carbon oxaloacetate. Now, the oxaloacetate in the mitochondria is converted to malate. So, oxaloacetate is converted to malate, and the malate will move out of mitochondria into the cytoplasm. So, all this is going on in the mitochondria. It will move out into the cytoplasm, malate comes out, and malate in the cytoplasm is converted back into oxaloacetate, and oxaloacetate is converted to phosphoenol pyruvate, this is a 3 carbon TCA glycolytic intermediate. So, in this reaction there will be removal of carbon dioxide, and also there is a need of GTP in this reaction. So, there is a GTP is necessary to conduct this reaction. GTP is needed into the reaction, GTP gets into the reaction. So, that is how oxaloacetate is converted to phosphoenol pyruvate. The reaction is catalyzed by enzyme phosphoenol pyruvate carboxykinase. Name of the enzyme is phosphoenol pyruvate carboxykinase. So, that is an enzyme here. So, basically 2 enzymes which converts pyruvate coming from alanine. So, of course, alanine transaminase is needed there. So, pyruvate carboxylase and the phosphoenol pyruvate carboxykinase. So, these are the 2 high yield enzymes that you need to remember. Once you get phosphoenol pyruvate, you know, like it can be reversed into glucose molecule. Okay, so how it will be reversed into glucose molecule? Let me explain that. So, same thing it will be applied for even conversion of lactate into glucose also. So, I am going to erase all this. So, I am going to retain my phosphoenol pyruvate only. So, we have phosphoenol pyruvate here. So, phosphoenol pyruvate into pyruvate molecule. So, phosphoenol pyruvate, it is phosphoenol pyruvate is converted to, of course, you need 2 molecules of phosphoenol pyruvate. Phosphoenol pyruvates are converted into 2-phosphoglycerate, 2-phosphoglycerate is converted to 3-phosphoglycerate, 3-phosphoglycerate is converted into 1,3-bisphosphoglycerate, that is 1,3-BPG, and 1,3-bisphosphoglycerate is converted into glycerol-dehyde 3-phosphate, and of course, all these are 2 molecules. Now, the glycerol-dehyde 3-phosphate 2 molecules, they will be converted into fructose 1,6-bisphosphate 1 molecule, because it is a 6 carbon. Together 2 glycerol-dehyde 3-phosphate which have got 3 carbon each will be converted to fructose 1,6-bisphosphate. Now, the fructose 1,6-bisphosphate is converted to fructose 6-phosphate. This will be done by enzyme fructose 1,6-bisphosphatase, fructose 1,6-bisphosphatase. So, this is the enzyme that converts fructose 1,6-bisphosphate into fructose 6-phosphate. Now, the fructose 6-phosphate is converted to glucose 6-phosphate, and glucose 6-phosphate will be converted into glucose, and that will be done by glucose 6-phosphatase enzyme, glucose 6-phosphatase. So, that means we need 2 enzymes here, conversion of fructose 1,6-bisphosphate into fructose 6-phosphate to fructose 1,6-bisphosphatase, and glucose 6-phosphate into glucose 6-phosphatase. So, this is how alanine is converted all the way into glucose molecule. So, just to quickly recap, so we have alanine converted into pyruvate, and pyruvate is converted into oxaloacetate. Oxaloacetate is converted into phosphoenol pyruvate. Okay. So, I just condensed all the reaction which I have explained previously. So, pyruvate into oxaloacetate, we have pyruvate carboxylase enzyme, and oxaloacetate into phosphoenol pyruvate, we have PEP CK carboxykinase, phosphoenol pyruvate carboxykinase. So, and then we have, so these are the 4 enzymes now you are seeing. So, as you can see, pyruvate carboxylase, phosphoenol pyruvate carboxykinase, fructose 1,6 bisphosphatase and glucose 6 phosphatase. These are the enzymes that are needed to convert 2 molecules of alanine into 1 molecule of glucose. This is how alanine is converted to glucose. Now, how lactate is converted to glucose? So, let us look into that. All you need to do here is you just change alanine. Instead of alanine, you write lactate now. So, alanine is not there. So, now let us say write lactate. How lactate is converted to glucose? So, we need 2 lactate molecules to be converted into glucose, and lactate is converted initially to pyruvate by lactate dehydrogenase enzyme, which I have already explained you. So, once you get 2 lactate converted into 2 pyruvate, of course, these are all 2 molecules, these 2 pyruvate, so that is lactate dehydrogenase. After that, pyruvate is converted to oxaloacetate by pyruvate carboxylase, and oxaloacetate into phosphoenol pyruvate by phosphoenol pyruvate carboxykinase, and then we need a fructose 1,6 bisphosphatase, glucose 6 phosphatase. So, to convert 2 lactate into 1 glucose, you need 4 important gluconeogenic enzymes, that is pyruvate carboxylase, phosphoenol pyruvate carboxykinase, fructose 1,6 bisphosphatase, glucose 6 phosphatase. Of course, you need lactate dehydrogenase in the very first conversion of lactate into pyruvate. Okay. So, that is how lactate is converted to pyruvate molecule. Now, let us see how glycerol is converted into glucose molecule. So, I am going to erase all the lactate conversion enzymes, alanine conversion enzyme, because you do not need them for conversion of glycerol into glucose molecule. So, I am just taking them, all of them now. So, directly let us go into, so I am going to take you directly into conversion of glycerol into glucose molecule. So, glycerol coming from adipose tissue, glycerol is a 3 carbon molecule. So, this glycerol is converted to glycerol 3 phosphate, and that will be done by glycerol kinase enzyme, and glycerol 3 phosphate will be converted into dihydroxyacetone phosphate, DHAP, dihydroxyacetone phosphate. So, this will be done by enzyme glycerol 3 phosphate dehydrogenase. I already explained this reaction need NAD plus to continue. So, we have 2 molecule of glycerol converted to 2 molecule of glycerol 3 phosphate becoming 2 molecule of dihydroxyacetone phosphate. In that, 1 molecule of dihydroxyacetone phosphate is converted to glyceraldehyde 3 phosphate. So, there will be formation of glyceraldehyde 3 phosphate. So, I am going to take 1 molecule out. So, 1 molecule of glyceraldehyde 3 phosphate. So, and then 1 molecule of dihydroxyacetone phosphate. So, basically we have 2 now. One is dihydroxyacetone phosphate, other is glyceraldehyde 3 phosphate. They both combine now, glyceraldehyde 3 phosphate and dihydroxyacetone phosphate. They both combine to make fructose 1,6 bisphosphate, which is converted to fructose 6 phosphate, and that will be converted to glucose 6 phosphate and glucose. So, overall conversion of glycerol into glucose, 2 glycerol into 1 glucose, you need glycerol kinase, glycerol 3 phosphate dehydrogenase, fructose 1,6 bisphosphatase and glucose 6 phosphatase. So, these are the important enzymes that are needed for the conversion of glycerol into glucose molecule. Now, let us see our last molecule, that is conversion of propionyl CoA into glucose molecule. So, what all the enzymes that are needed in the conversion of propionyl CoA into glucose. So, for that I already explained you. So, how propionyl CoA enters into gluconeogenesis process in the previous reaction. So, all we need to get here is we need to convert propionyl CoA into succinyl CoA. Once you get succinyl CoA, so succinyl CoA is converted to fumarate, succinate into fumarate, and fumarate into malate molecule. So, let me explain that now. So, propionyl CoA coming from gluconeogenesis, that is Bob needs vitamin M. Propionyl CoA. Propionyl CoA is converted to succinyl CoA. Initially it is converted to methylmalonyl CoA. Propionyl CoA is converted to methylmalonyl CoA. Let me write that here. Methylmalonyl CoA, and methylmalonyl CoA is converted to succinyl CoA. Succinyl CoA is converted to succinate. Succinate is converted to fumarate. Fumarate is converted to malate, and malate is converted to oxaloacetate. Oxaloacetate is converted to phosphoenol pyruvate, and phosphoenol pyruvate is basically reversed into glycerol D3 phosphate, and glycerol D3 phosphate is converted into fructose 1,6 bisphosphate, and all the way after that. So, let us see what are the enzymes. So, propionyl CoA to methylmalonyl CoA, we have propionyl CoA carboxylase, and then we have methylmalonyl CoA to succinyl CoA, we have methylmalonyl CoA mutase. After that, other enzymes are there, TCA cycle enzymes. So, oxaloacetate to phosphoenol pyruvate, we have PEPCK, phosphoenol pyruvate carboxykinase enzyme, and then we have fructose 1,6 bisphosphatase, glucose 6 phosphatase. So, overall we need 5 important enzymes in the conversion of 2 propionyl CoA molecule. Of course, you need 2 propionyl CoA molecule, 2 molecules of propionyl CoA, because each of them are 3 carbon molecules. So, we have this propionyl CoA carboxylase, methylmalonyl CoA mutase, PEPCK, phosphoenol pyruvate carboxykinase, fructose 1,6 bisphosphatase, and glucose 6 phosphatase. These are the enzymes that are reversing or that are making glucose from propionyl CoA molecule. Alright, so now let me explain you approximately how many ATPs are needed for gluconeogenesis process. So, let me be very brief in this. So, conversion of say 2 lactate molecules, or say 2 alanine molecules, 2 alanine, either 2 lactate molecules going into 2 pyruvate molecules, or 2 alanine molecules going into 2 pyruvate molecules. So, there is no need of ATPs there. So, you need NAD plus and all that. So, let us just restrict ourselves with the need of ATPs. So, 2 pyruvates going into mitochondria becoming 2 oxaloacetate molecule. I will just write it as OAA, oxaloacetate. So, in this process there will be consumption of 2 ATPs, because pyruvate carboxylase reaction needs ATP. So, 2 minus, I will write minus 2 ATPs there. Now, the oxaloacetate, 2 oxaloacetate will be converted to malate going out becoming oxaloacetate. So, in the cytoplasm. So, I will write oxaloacetate in the cytoplasm, 2 of them converted to 2 molecule of phosphoenol pyruvate. So, in order to do that, you need 2 GTPs which are equivalent to ATP molecules. So, 2 GTP there. So, which are equivalent to 2 ATP molecules. So, 2 ATPs there, 2 ATPs, actually you need a GTP in that particular reaction. Now 2-phosphoenol pyruvate going into 2 molecules of 2-phosphoglycerate, 2-phosphoglycerate into 3-phosphoglycerate, 3-phosphoglycerate into 2 molecules of 1,3-bisphosphoglycerate, 2 molecules of 1,3-BPG, and 2 molecules of 1,3-BPG going into 2 molecules of glycerol dehyde 3-phosphate, and there you need again 2 ATPs. So, minus 2 ATPs, and after that there is no need of ATPs. So, glycerol dehyde 3-phosphate will go all the way to glucose molecule. There is no need of ATP anywhere. So, overall what you see here is conversion of 2 lactate into glucose or 2 alanine into glucose. There is a need of 2 plus 2 plus 2. So, there is a need of 6 ATP molecules here. So, 6 ATPs are necessary for the conversion of 2 lactate into 1 glucose or 2 alanine into 1 glucose, and all these 6 ATPs for gluconeogenesis will come from fatty acid oxidation. Remember that. So, gluconeogenesis process, it is supported by fatty acid oxidation, particularly beta oxidation. So, the beta oxidation of fatty acid is the energy source for ATPs that are needed for gluconeogenesis process. Remember that. So, now let us move on to see our one of the last concept here is pyruvate carboxylase deficiency. What actually happens in pyruvate carboxylase deficiency? Why pyruvate carboxylase deficiency can lead to signs and symptoms and all that. So, I have already sufficiently explained you pyruvate, the role of pyruvate here. So, in the gluconeogenesis process, see the alanine is converted into pyruvate, or lactate is converted to pyruvate. Pyruvate is converted to oxaloacetate by pyruvate carboxylase enzyme. Oxaloacetate has different fates. Oxaloacetate can go into TCA cycle to make citrate, or oxaloacetate can undergo transamination reaction to make aspartate, or oxaloacetate can go into gluconeogenesis process making glucose. Okay, so what if there is a deficiency of pyruvate carboxylase? So, that is what is our topic now. So, pyruvate carboxylase enzyme, it will be coded by PC gene. A gene that is coding for pyruvate carboxylase is PC gene, and if there is a mutation in PC gene mutation, that will lead to decrease in pyruvate carboxylase activity. So, when there is a decrease in pyruvate carboxylase activity, so obviously the substrate for pyruvate carboxylase is pyruvate. This is the substrate for pyruvate carboxylase. Product is oxaloacetate. So, with the decrease in the activity of pyruvate carboxylase, if the enzyme is mutated, what will happen is, so your pyruvate molecule, pyruvate concentration of pyruvate, it will increase because substrate is not consumed. So, the pyruvate concentration will increase here. So, there is an increase in the concentration of pyruvate will build up, and there obviously there will be decrease in oxaloacetate molecule. So, what happens with that? When the pyruvate is increased here, so this pyruvate is going back into alanine molecule because this is a reversible reaction done by alanine transaminase enzyme. So, what happens is alanine concentration will build up. So, there will be increase in alanine levels in the tissue, and later it will appear in the blood. So, there will be hyperalaninemia. Hyperalaninemia means excess alanine levels in the blood. And also note that when the pyruvate is building up, pyruvate can also go to lactate side by lactate dehydrogenase enzyme. So, the lactate will build up now. So, there will be build up of lactate in the blood. So, lactate builds up, that will lead to lactic acidosis because that will appear in the blood, lactic acidosis. Patient will have lactic acidosis. Now, that is what happens. Now, let us see the other side. Pyruvate converting into oxaloacetate when the enzyme is deficient. So, oxaloacetate decreases, because in the decrease in the oxaloacetate, what will happen is, so the citrate will also decrease, because the TCA cycle is the one that is needing oxaloacetate to combine with acetyl CoA to make citrate. I have a video on that. So, site rate decreases means TCA cycle decreases. So, decrease in TCA cycle means decrease in ATP formation, because TCA cycle is needed for ATP generation. So, imagine this, if this goes on in the skeletal muscle. So, muscle will break open, because lack of ATP in the skeletal muscle will basically break the skeletal muscle, leading to skeletal myopathy. And the skeletal myopathy means like protein present in the skeletal muscle will break open, and it will lead to hyperalaninemia. Excess alanine will present in the blood, and also patient will have hypotonia, muscle tone decreases, hyperalaninemia, hyperalaninemia, consequence of decrease in TCA cycle. And also note that oxaloacetate is the one that is converted to aspartate by aspartate transaminase enzyme. During that reaction, so there will be glutamate entering into the reaction, converting alpha ketoglutarate. That's how make aspartate. So, what happens is, when there is a decrease in oxaloacetate, so that will lead to decrease in aspartate, and actually eventually there will be decrease in transamination reaction, giving rise to decrease in glutamate. Note that especially in the central nervous system, both aspartate, decrease in aspartate or decrease in glutamate, it will give rise to mental retardation, neurological degeneration, mental retardation can be seen here. And on the other side, oxaloacetate is going into glucose by gluconeogenesis process. When there is a decrease in oxaloacetate, so that will also decrease in glucose formation. So, there will be decrease in glucose, that will give rise to fasting hypoglycemia. So, low blood sugar level. So, these are some of the signs that you are going to see in pyruvate carboxylase deficiency. So, what are the signs that we see? So, there is increase in alanine level, so hyperalaninemia, lactic acidosis, skeletal myopathy, hyperammonemia, not alaninemia, hyperammonemia, excess ammonia level, hyperammonemia, and hypotonia, mental retardation, and fasting hypoglycemia. So, these are the signs that you are going to see in pyruvate carboxylase deficiency. So, that is a hyperphenylalanemia, lactic acidosis, hyperammonemia, then hypotonia, mental retardation, and fasting hypoglycemia. So, all these are because of decrease in pyruvate carboxylase enzyme deficiency. Okay. So, that is all about gluconeogenesis process. I have a video on regulation of gluconeogenesis, regulation of gluconeogenesis. So, regulation of gluconeogenesis, I have a separate video on that. The link for that video is appearing right now in the upper right corner here. So, please watch that video. That's about it, and if you like the video, so please like it, and if you have any comments or any questions, so put that in the comment section. And if you haven't subscribed to this channel, so please consider subscribing to this channel, and also click the bell icon so that you get regular notification. So, that is all for now. I hope this video has helped you in understanding gluconeogenesis. I will see you in my next video. So, till then, you take care.